be talking about my project, which is evolving neural networks for artificial life in artificial ecosystem. I'm going to introduce you to Neuro-Evolution, which is the main focus of my project. I've implemented 4 Neuro-Evolutionary algorithms, and we'll talk about those as well. I'll briefly go through methodology, because that is something you need to discuss when you do your third-year projects. And then we'll conclude by looking at the results and analyzing the meaning of that. And finally, just a little bit on future work, which is also something that you'll look at in your third-year projects. So to start off, by artificial life, I basically mean the study of systems that emulate life in a digital way. So these can often be using a subset of real-world constraints, but sometimes you can add new constraints to those worlds. So agents in these worlds are essentially the creatures, the agents that live there, and they can make decisions based on their senses of that environment. So for just a couple examples, we have the bibits, the top picture here, which I'll show a little video of in a moment. It was a big inspiration for my project. And on the bottom here, we have the more familiar Conway's Game of Life.
So this is a little clip from the bibits. This is not my project, but to give you an idea of how complex artificial life can be, here we're seeing a bunch of agents releasing pheromones, eating foods. Here they're attacking each other. The options and sort of possibilities of this environment are endless. So in my artificial life simulation, I have agents, which look like this, and we have food, which looks like this. So the agents have a neural network to control their actions, the inputs of which mimic their senses. So they have a constant input, they have access to their age, their current energy, the sign of age, which gives them the ability to react in sort of repeating behavior. And they have angle and distance nearest food, like so, distance as well. And their outputs of this neural network control their movements, their actions. So this could be to move forward or to rotate, for example, to move towards food. So a good question now is, why would you bother with neuroevolution over traditional neural network training? And it's because choosing the structure of a network can be the hardest part of artificial learning. Choosing a poor structure can lead to poor performing networks or excessive cost and time to train that network. If you choose a structure too small, you risk never being able to train that network to recognize the behavior you're looking for. So neuroevolutionary algorithms are based on evolutionary algorithms, but with a focus on neural networks. And they develop structure and weights of these networks over time based on Darwinian evolution. So the 4 algorithms that I'll be looking at and I have implemented are neuroevolution of augmenting topologies, real-time neuroevolution of augmenting topologies, phased pruning, and hyperneat, which is a hypercube-based version of the first algorithm. They're all quite similar, so I'll cover the first one in a bit more detail, and then I'll discuss the differences of the following 3. So with neuroevolution of augmenting topologies, we start with a minimal structure. We want these networks to be as simple as possible. By starting minimally, we only add features that appear to benefit the structure. For my case, I've used a network with inputs and outputs, no hidden layers and no connections. Obviously, this means the network does nothing initially. So the process follows like so. We take our networks and we evaluate them against a fitness function. The fitness function I've used is the energy of the agents divided by their age, which is essentially how much energy they are acquiring per time unit. We then speciate them, which is a process where we group agents that are considered similar, and we do this based on their network structure. So basically, agents with shared connections will be considered more similar than those that have very different structures. We then move the genomes of the fittest agents to the next generation without modifying them. That is to preserve those high-performing agents and not risk mutating them away from being high-performing. And that's called elitism. Additionally, we cull the weakest of the agents, which basically prevents them from passing on their genetic information. We prevent them reproducing, basically. Finally, we probabilistically choose parents for reproduction. Some of this will be done sexually, which is to cross over 2 networks. Some of it is asexually, which is to simply mutate an existing network. So some examples of these mutations are as follows. When we asexually reproduce a network, we can form one of these 3. One of these 3 mutations, sorry. So we can adjust the weight of an existing connection in a network, like so. We can take 2 nodes and we can add a new connection between them, like so. Or we can take an existing connection, remove it, and replace it with a node with 2 connections between them, like so. So you can see how starting with a completely empty network, we can end up with a network of varying structures based on these mutations. But additionally, we have sexual reproduction. This is a variation of the crossover function in evolutionary algorithms. And the goal is to take these 2 networks, which we've deemed to be well-performing, and produce an offspring that is also well-performing. But looking at these structures, it's very difficult to figure out how to combine them in a meaningful way. If we do it poorly, then we risk losing the performance benefits that the structures have given these networks. And if we do it too loosely, then we risk just sort of adding too much structure unnecessarily. This is called the competing conventions problem because both networks can represent similar desired outcomes, but with very different structures. The way that NEAT deals with this issue is to represent these networks, instead of in a traditional way, with lists of genes. So here we can see the connection genes for these networks. You can see innovation numbers on the top. Innovation numbers are evolved when a connection is first mutated into existence and it's passed down through generations. That means it can act as a historical tracker for when that gene first occurred, and we can link genes to each other and determine they have common ancestors through those. The bit below shows which nodes the connection goes between. We can also see some are disabled, which means they're not represented in the network. So what we do with these lists is we cross them over like so, lining them up based on innovation number. So you can see there are a few that have been skipped in the first parent because they don't have a matching innovation number to the second parent. We then randomly select these genes from those that are shared, shared meaning they have the same innovation number, and we take all of the excess and disjoint genes from the fitter parent. In this case, they've been considered equally fit, so we take all of the excess and disjoint. And you can see on the right there the resulting gene list from this. From that gene list, we can reconstruct a new network, which, as you can see, has many of the features of both the 2 parents, but represents the same thing in a more meaningful way to itself. The second algorithm here is real-time neuroevolution of augmented topologies, which is very similar, except it focuses on modifying the algorithm to be useful for real-time environments. So this could be during gameplay. We could be evolving NPCs or opponents without a user noticing sudden changes in the behavior of the enemies they're fighting. The algorithm was actually first introduced in a game called Nero, where you would evolve robots in a combat environment to fight another player's evolved robots. Like I said, it aims to modify the behavior in real time so that it can counter weaknesses that the player might be exploiting too heavily. So how does this algorithm work? Well, instead of replacing the entire population at a time, as we do in NEAT, we simply select one of the agents that we deem to be a weak agent, and we choose a new species from the remaining agents to be the parent of our new agent. This is based on the adjusted fitness, which is essentially the fitness of these agents adjusted for their age and their species. So large species are given a negative bonus, I guess, so they are less likely to be picked because there's already a lot of them. We want to favor the smaller species to give them a chance to prove to be well-performing. We then use this parent to create a new child. This could be sexually or asexually, and we hope that that agent will do better, and we put it into the simulation. Phase pruning is a modification of the NEAT algorithm that aims to limit the complexity of agents. So I've defined complexity as the sum of the number of nodes and number of connections in a network. And the goal of phase pruning is to reduce this so that evaluation can be performed quicker and that we can search the lower dimensionality search space more efficiently. So because of my environment, I'm testing agents for 30 seconds by default. And so there isn't really a benefit to making simpler networks that can be evaluated quicker. They're going to be evaluated for 30 seconds regardless. But in environments where the evaluation speed can be a factor on the learning rate, this would be a positive. The way the algorithm works is it performs regular NEAT until the agents reach a threshold complexity. At that point, we swap the additive mutations, which are the ones I showed you earlier, with destructive mutations. So these are potentially removing connections, or replacing a node with a connection crossing that bridge instead. Additionally, we only allow asexual reproduction because sexual reproduction could repropagate previously destroyed structures back through those networks. The final algorithm that I've implemented is HyperNeat, and this algorithm aims to bridge the gap between the neural networks we have currently and the human brain. It does this by using what's called an indirect representation. This means that each gene in a genome can represent 0, 1, or many structures in the final network. This means that they can be much larger with a very small and compact representation still. So to do this, we evolve using NEAT a different neural network called a compositional pattern producing network, or CPPN. We also define a substrate, which is a maximal set of neurons from which the final network can consist of. And we give each neuron in that substrate a coordinate. So the CPPN is a network that has 7 inputs for my example, because I'm using 3 dimensions. So we have an input for each dimension of each pair of neurons. So that's 6, and then we also add a bias. 7 inputs, a single output. This structure is evolved through NEAT in the same way that I discussed for the agents. But we pass in, for every pair of neurons in the substrate, their coordinates, and we take the output of our CPPN. If the output is above a threshold, if the magnitude of the output is above a threshold, then we create an edge in the substrate between those 2 neurons with a connection weight, some multiple of that output. Following this process on every pair of neurons, the substrate is the neural network that the agents use as their brain. The benefits of HyperNeat is that it's able to harness the relative location of sensors and outputs. It has a better understanding of sensors that are next to each other and that are taking information next to each other. Therefore, it can recognize that 2 inputs that are reading from the same place are more meaningful together than 2 from 2 separate locations. Additionally, because of this indirect representation, we can change the substrate without having to retrain the network. The CPPN can work on a different substrate with a relatively guaranteed fitness. So onto some methodology. I'm not going to bore you too much with this, but it is something you need to discuss in your projects, and it's worth thinking about early on how you're going to plan your project. Give yourself enough time to complete the tasks and do it in an order that makes sense for the project. So for example here, potentially a little bit of poor planning on my part, I aimed to save the system before I'd implemented any of the evolutionary algorithms, so there wasn't very much to save. In terms of development process, this is something else you should be thinking about. I tried to use an iterative project development methodology, which means that I could develop my environment first and then slowly add features to it, such as the agents, each algorithm following each other, kind of like so. And this also means that in future, if I want to extend this project, add some more algorithms perhaps, I can do this without having to change what I've already implemented. Additionally, the program is robust to the changes in requirements of the agents. If I decided to give my agents some more inputs or give them some more actions to perform, the neural networks that are being evolved can still be evolved using the same algorithms. There is no requirement that each network has a set number of inputs or outputs. So now we'll move on to some experimental results to see how these algorithms compared, I guess. The first thing to note is that I've logged data every time an agent is replaced. As we discussed, RT replaces agents much more frequently. So the generation numbers you see are much larger, but they represent the same amount of time. Additionally, if you see this graph here, RT-NEAT agents can persist for longer than a set time. So while NEAT agents may only persist for 30 seconds, RT-NEAT agents can persist much longer, provided they are still proving to be fit. If we don't normalize the fitness of these agents by their age, this means that agents that are consistently eating food are considered increasingly fit. But this is not true because their networks aren't changing. And you can see here that the older agents just become more and more fit to the point that newer agents have no chance of competing with them. So for the NEAT algorithm, I've got 2 different runs here. The left and the right are group graphs. On the top, we see the fitness of these agents. And the bottom, we see the complexity of these agents. So because NEAT only has additive mutations, the complexity continues to rise near linearly. despite the fact that the fitness is quickly plateauing when the agents become as fit as they can in this environment. On the side here, you can see the max mean fitness was averaged to be just under 1.5 for these two runs. And the complexity, it varied quite a bit, but it was quite large regardless, between 90 and 50. The plateau is a point where I've considered where the agents have reached within 5% of their maximum fitness. And this is to account for the fact that at this plateau, they still fluctuate a little bit. For the RT-NEAT algorithm, we see some interesting results here. There are many more peaks in this fitness, despite the fact that the max mean fitness is only slightly larger. I determined that these peaks were due to new agents being created and placed directly on top of food, meaning they would eat it immediately and have a very, very small age. Since their fitness was their energy divided by their age, this had a multiplicative effect, meaning their fitness went very, very high very quickly. But regardless, if we follow the sort of orange trend, it is slightly larger than NEAT, but not as high as the blue peaks would suggest. Interestingly, despite the fact this algorithm has no destructive mutations, the complexity seems to plateau a little bit. It reaches around 35 without going much higher than that, which is significantly lower than the NEAT algorithm. For the phased pruning algorithm, we see some more interesting results. Perhaps expected here, the complexity rises and falls. This is due to the fact that the pruning phases begin and we start stripping away the structure. You can see that it comes in cycles because it strips away until the fitness no longer remains equal, essentially, determining that we have taken away too much structure and we need to start adding it back. You can see here that in the fitness graphs, the plateau is reached at very different times. This is because in the first run on the left, we can see the pruning has been too harsh. It's pruned the beneficial structures away very early, and it has prevented the agents from gaining their advantage, getting a good fitness level. And it's delayed their evolution quite significantly. Regardless, they have very low complexity at the end. We can see around 40 to 50, which is significantly lower than NEAT as well, but their fitness is very, very similar to NEAT, that is. In the final algorithm here, we have hyper-NEAT. And this one, it's a little bit of a shame to see, but their fitness is significantly lower. It looks similar, but you can see on the axes there are about 0.5, just about averaging 1. Additionally, the CPPN complexity, this is the complexity of their CPPN I mentioned earlier, not the complexity of the agents themselves. Because it is evolved using NEAT, the complexity here looks very similar to that of the NEAT algorithm. But it may be more interesting to look at the complexity of the agents themselves. So here we see a very, very sharp increase in complexity very early, and it's maintained throughout. This complexity is around 900. This is because the substrate is much larger than the genomes that were evolved by the other algorithms. And additionally, excess connections within the substrate has no negative impact on the performance of the agents unless it reaches the end. So there's less incentive for these substrates to be too simple, or simple enough, I guess. Great, so to draw some conclusions from this, we can see that NEAT and phase pruning perform very similarly, but phase pruning produces less complex agents, with the cost of it taking slightly longer. RT-NEAT provides the highest fitness agents, even when we ignore those lucky agents that are just eating food as soon as they're created. It also has the broadest range of applications because we can use it in a real-time environment, meaning we can interact with the agents as they're evolving. It has a very simple implementation, and my favorite point about it is it has an implicit indefinite life preparation stage. So essentially, we are preparing these agents to exist for an undefined amount of time, regardless of the fact that we're testing them in an environment where we obviously can't allow them to live forever. The hyper-NEAT algorithm was the most complex to implement, and provided very low fitness, which was unfortunate in this environment. But it is just a result of this environment not having the kinds of inputs and outputs that hyper-NEAT can benefit from. So all measurements were taken from a single point, meaning it was not able to utilize their coordinates as relative offsets from each other. It could not recognize that one sense was related to another in some way. if the genomes were given more advanced inputs, for example, like array-based vision, we'd hope to see some sort of improvements there based on them recognizing two rays that are next to each other. So in terms of future work, there are many other algorithms that we could implement. So for example, hyperneat could be extended to ES hyperneat, which is evolving substrate hyperneat. This would allow the substrate that I mentioned to be evolved alongside the CPPN, which means that neurons in the CPPN can be placed at coordinates that benefit the structure of the network itself and are not confined by the constraints that I've placed on it. We could additionally try fusing the three algorithms that I've discussed other than neat today to get phased hyper-RT-neat. Be interesting to see if that could be done and the effects of that. Furthermore, it could be more interesting to increase the complexity of the simulation instead of the algorithms to see how they can handle increasingly complex environments. So for example, I've mentioned increasing the range of activation functions that can be used, addition of genes that may be things like an agent's base speed, so that some agents can specialize into being faster while others might be stronger. Or we could think about increasingly complex systems such as digestive systems, which might encourage agents to store their food rather than eating it immediately, which may lead to them fighting over these stores that they've made. Thank you for listening.